Hello students, this is Professor Chalai, and in this video we're going to look at molecular polarity and dipole moment. As always, you can follow along with our Chapter 7 workbook. By the end of this video, you should be able to describe polar molecules and also assess the polarity of various molecules. Let's get started. Alright, so what do we mean when we say we have a polar molecule? Well, earlier we talked about polar bonds, right? Where it depends on the electronegativity of the element. For example, let's look at a carbon-oxygen bond. We know that oxygen pulls on electrons more than carbon, so this oxygen will have slightly more electrons than the carbon, and so what we end up having is a polar bond. And we usually draw this little arrow with a little stick through it to show the direction that the electron's being pulled in. So this is a polar bond. However, while individual bonds could be polar, it doesn't mean that the whole molecule will be polar. For example, let's look at carbon dioxide, right? We know that carbon dioxide is made up of two carbon-oxygen bonds. So we know that definitely this bond is going to pull a little bit of electron that way, and this one is going to pull electron that way. So if you think about the charges, that's going to be slightly negative, that's going to be slightly positive, that's going to be slightly negative. So this carbon dioxide here has polar bonds, but overall the molecule is not polar. And why that is because we looked in our previous video and see that this geometry here is a linear geometry. These bonds are separated by 180 degrees. They're exactly in opposite ends, sides of each other. So as a whole, this oxygen pulling electrons to the right and this oxygen pulling electrons to the left will leave this molecule as not polar because those two pulls completely and perfectly cancel each other out, right? If you think about vectors, if you remember our math on vectors, to add up two arrows, you draw them head to tail. So the head of this one becomes the tail of the other one. And so if you add up these two arrows, right, let's say you started with the one on top, draw the arrow going to the right, which is this one right here. And then from the head of this one, you draw the other arrow, which is the one going to the left. You end up here, and so you end up exactly where you started. So you added up those two polarities, and you get 0 for the overall molecule. So this is not polar. However, if you had a situation where maybe this was, I don't know, a molecule like this, same carbon, same oxygen, slightly negative, slightly positive, and it's pulling the electrons that way. The carbon-hydrogen bonds are not polar. There's nothing to cancel out this polarity, so what we end up having is a polar molecule. So polar molecules are simply molecules with a net dipole moment. What does that mean, net dipole moment? It means that when we add up all of their dipole moments for every single bond, they don't cancel each other out, but there is some dipole moment. So if I were to draw the dipole moment of this whole molecule, it will be the same as the one for that bond. The dipole moment for this whole molecule is 0 because they perfectly cancel each other out. So if we want to figure out whether molecules are polar or not, we need to draw them, draw their Lewis structures like we did here, figure out their geometry, right? Because if carbon and oxygen was like this, which we know it's not, and this was pulling this way and this was pulling this way, if we added up these two arrows, right, adding it head to tail, our net dipole moment would start from here and go here. It would not be 0. If carbon dioxide was bent, in this example, it would be polar, but we know that carbon dioxide is linear, so it's not polar. So here's some tips in trying to figure out whether a molecule is polar or not. You need to draw the Lewis structure first. And you're probably realizing this is true for a few of the topics that we've covered in this chapter, because guess what? This chapter is focused a lot on Lewis structures. Then you need to figure out whether the molecule has any polar bonds, and then based off of the geometry, whether those polar bonds cancel out or not. So I'll do one more as an example for you. I'll do number 19 as an example for you, and then you can try to figure out 20, 21, 22 by yourself. So already we know that water is polar, but let's just do the entire exercise just to be sure. So let's draw the Lewis structure for water, right? Oxygen has 6 valence electrons and hydrogen has 1 each. So we need not 18, but 8 electrons, valence electrons. There's already 4 in bonds, so we need to add 4 more. And we're going to give them to oxygen. So right away, this is our Lewis structure for water. Now we need to figure out the geometry here. Is it in a straight line? Is it bent? What's going on? Let's count the electron groups around the oxygen. There's 1, 2, 3, 4, right? 4 electron groups and 2 of them are bonds. So let's go all the way up here. And since this has gotten so confusing, I'll erase a lot of this. 4 electron groups, 2 of them are bonds, which means that while the electrons are tetrahedral, the structure, the geometry is bent with a 109 or less than 109.5 degrees. So let's look at water again. So really, these 2 bonds should not be in a straight line. If I were to redraw them, right, it should be bent with an angle of less than 109.5 degrees. And then we have the 2 lone pairs sticking out somewhere. So this is our water structure. Now let's look at the polarity. We know that oxygen and hydrogen is polar because oxygen is very electronegative. It'll pull electrons this way and that way. So if we added up these 2 vectors, right, let's look at this one first, the one on the left. And then we add the one to the right, head to tail, remember? So overall, we end up with a polarity that goes this way. So if we want to look at the polarity of this whole molecule, it points away from the hydrogen towards the oxygen. And that means that this oxygen will be slightly negative, these hydrogens will be slightly positive. There it is. Water is polar, and we just proved it. Okay, try ammonia by yourself and we'll see what we get. Okay, let's look at ammonia. We know that hydrogens are always going to be terminal, so we can put the nitrogen in the middle. All right, nitrogen has 5 electrons, valence electrons. Hydrogen has 1, and there's 3 of them, so that gives us 8 valence electrons, and we have 6 already taken up in bonds, so that'll leave us with 2. And we can only put those 2 on nitrogen because hydrogen can't fit more. They already have 2 from the bonds. Let's look at the structure here. The center atom has 1, 2, 3, 4 electron groups. 3 of them are bonds. So 4 electrons, 3 bonds, that would be a pyramidal, trigonal pyramidal structure. But where it is, just to prove it to you, 4 groups, 3 of them are bonds, is a trigonal pyramidal structure. And just to remind you what that is, let's open up our little structure here. 4 groups, 3 of them are bonds, and 1 is a lone pair. This is our trigonal pyramidal structure. So this is what ammonia looks like, right? Where the purple atom could be the nitrogen, white atoms are the hydrogen. So let's scroll back down. If I were to draw this realistically, it would be nitrogen here and our 3 hydrogens sort of sticking down and the lone pair sticking up like this. Okay, what about polarity? Well, nitrogen is slightly more polar than hydrogen. Nitrogen slightly more polar. And if you add up, well, you can already see that all of these are going to add up and pointing towards the top, right? Because they're all sort of pointing inwards into the top. So they'll point straight up, and so we end up with a polar molecule. Water is also polar. Let's look at CF4, whether it's polar or not. We draw the Lewis structure. Again, if you haven't done this already, please do so first. CF. F is terminal because it's very electronegative. And let's look at valence electrons. Carbon has 4, fluorine has 7. There's 4 of them. 7 4 is 28 plus 4 is 32. We have 8 in bonds, so that means that we are left with 26 if my math is correct. So let's put those 26 electrons on our fluorine to start with. 2, 4, 6, can't fit more. 8, 10, 12, can't fit more. 14, 16, 18, 20, 22, 24. That's all we have time for. Okay. I think that's all we have time for. Did I do my math correctly? Yeah, 32 minus 8 is 24, not 26. Sorry about that. All right, so this is our Lewis structure. Let's look at the polarity. We know fluorine is very electronegative, so it's going to be pulling on all of these bonds. But let's see if they cancel out or not. We have 4 groups, no lone pairs. So as you already know, 4 groups, no lone pairs, that's a tetrahedral structure, right? So 1, 2, 3, 4, where all of the bonds are the same angle from every other bond, right? Do you see that? So they're all going to pull on each other in the opposite direction, and they're going to perfectly cancel because all the bonds are the same angle away from each other. So these are going to pull equally in all directions, and CF4 is going to end up being non-polar. Finally, let's try N2O. We had done the Lewis structure for this earlier, but if you haven't done so yet, please do so again. We started with a structure like this. Let's count valence electrons. We have 5 from the nitrogen times 2 plus 6 from the oxygen. That gives us 16. We already have 4 from the bonds. That leaves 12 to share out. We can put 2, 4, 6 on the oxygen and another 6 on this nitrogen, and that's it. The center oxygen only has 4, it needs 4 more. So we talked about how we can borrow sort of 2 from the left, or 2 from the right, or 1 from the left and 1 from the right. And we talked about how some of those are more stable than the others. So let's look at that. Let's look at that situation. So if we borrow 2 from the 2 pairs from the left, we formed a triple bond. That was one possibility. Okay, the second possibility was we borrow 2 from the right. Well, we talked about how this one would probably not be possible because of the formal charges. And then finally, there's a possibility of sharing 1 each from the left and the right. So we have this situation. Oxygen pulls on electron more than nitrogen. Whereas in this, these two here, nitrogens, they have equal electronegativity, so we won't have a dipole bond set up there. And so what we end up having is a polar molecule. Okay, so that will bring us to the end of this chapter. Just to summarize what we talked about, molecules with a net dipole moment will be termed polar molecules, and net dipole moments means that their polar bonds don't cancel out, they actually add up. We did an example of water, right, where we found that water is actually a bent structure and their polarity does not cancel, so they actually add up. So water is polar. Ammonia, we also did the same example. Ammonia is polar. CF4, while fluorine is very electronegative, is not polar because it's tetrahedral and it pulls in it equally in the 4 directions. And we looked at N2O, while a complex molecule with resonance structure, NO is a polar bond and N is not. This is a polar molecule. All right, in our next set of videos, we'll begin chapter 8. I'll see you then. Bye.